3, 2, 1. All right, so welcome everybody. So this is the second talk in the Center for Deep Learning seminar series. So we are very excited to have today with us Stephanie Kermer. So Stephanie is a senior data scientist at Saturn Cloud, a company making large-scale Python easy and accessible to the data community using Dask. She has applied machine learning and data science in a number of industries, including as a data science technical lead at a travel data startup and as a senior data scientist at Uptake, an industrial data science company. Before joining Uptake, she worked on data science for social policy research at the University of Chicago and taught sociology and health policy at DePaul University. She has her website, www.stephaniekermer.com. So please feel free to go on her website and learn more about her outstanding career. So I think her talk is very timely because I've been hearing about Dask quite a lot in the last year or so. So it's definitely becoming more and more, let's say, popular and important at the same time within the data science community. So it's going to be great for all of us to learn more about Dask, and hopefully, I guess Stephanie's one goal of Stephanie's talk is probably to promote Dask and make many of us then use Dask in the future. All right, so with this being said, again, let me welcome Stephanie, and Stephanie, we are all looking forward to this next 45 minutes. So if you have questions during her presentation, please feel free to post them on chat. So Stephanie will try to pause once in a while and address those questions. Okay, but there will be time at the end also to ask questions. All right, so Stephanie, go ahead, please.
Great. Thank you so much, Diego and Yune, for having me today. I'm really excited to be here and to talk to you all. I am going to be talking about Dask and the ways that you can use Dask in concert with deep learning to really accelerate the training process without any reductions in the quality or the learning rate, that kind of thing. And so what I'm going to go through today, and let me share my screen so that you can follow along. I'm going to go through a few introductory slides first, just to tell you a little bit about Dask, about the sort of underlying concepts around parallelization in Python, which I think are important to understand before you get too deep in the weeds on applying it to deep learning. I'll talk a little bit about why you might want to apply this, why it would be relevant or useful in the deep learning context when you're already perhaps using a single node GPU, which is a lot of power already. Why would you need to add multiple GPUs and put them together and go even further? And then I'll go through a demo. I'll run some code to show you a little bit about actually what the process looks like of engaging in a distributed training task, a single task, but distributed training in PyTorch on a GPU cluster. So we'll get to see the whole thing. And then I'll show you some, because it might not finish in the time that I'm talking. I'll show you some results of model training processes that I've saved from previous training runs, so that we can see actually what the training sort of learning looks like in some examples. So that's the plan for today. And as Diego mentioned, if you have questions, please drop them in the chat. I'll every so often pick up some. I'll pause to make sure that we're all on the same page. And then at the very end too, I'll have plenty of time to answer questions and to sort of engage on whatever scenarios you're working on, situations that you may have run into with Dask and deep learning that you would like to chat about. I'm totally happy to get into all of that. If after everything is all done, you come up with a question you didn't think of in the moment, or you didn't want to, go into in the group, I'm on Twitter. You can see on screen my Twitter handle is data_Stephanie, and I'm always happy to engage on Twitter as well to talk about data science or talk about deep learning, whatever is on your mind. I'm also just to give you a heads up, I'm going to talk a little bit about Saturn Cloud and use some Saturn Cloud tooling in order to do the deep learning that were the training job for the demo. If you're interested in learning more about Saturn Cloud, we make GPUs, CPUs, and clusters for Dask accessible to anybody. There's a free level plan that gives you 10 hours of GPUs every month just for free. No strings attached, no price tag, nothing. So saturncloud.io is our website. Please check it out if this is something that you might be interested in, even if you just want to noodle around and play with it and see what it's all about. It's a very cool tool. It's very exciting infrastructure, and it makes all of this stuff a lot more accessible to any user, regardless of how much DevOps experience you might have. One last thing before I move on. The GitHub link that's on the screen is a GitHub repo that I'm keeping the materials for this sort of topic that I talk about at different occasions. I gave a talk earlier in February that's sort of adjacent to this, not the same. So there's 2 talks in that repo, both about PyTorch with GPUs and clusters. There's a folder called Center for Deep Learning, which you can find, and then you'll be able to see all of the content as I go through it, all of the code. These slides are all made in Jupyter Rise, so you can see everything that I'm doing as it goes through. Okay, now we can move on. So, talking about Dask, the thing that I want to get across is sort of just the general gist of what it is. If you're not familiar with it already, you may have heard of this as, say, an alternative to Spark, an alternative to, obviously, single node serial Python. And that's a good way to sort of think about it. Dask is an open source framework that builds on Python to enable parallelization of Python code. As I said, open source framework, it's free to use. There is no proprietary Dask ecosystem that you would need to buy into. And so that is one of the things that makes it really exciting to me, that this tool is it's very well managed. The management team, the development team is very attentive, and they're developing a lot, and it's really making a lot of progress in feature development and that kind of thing. And the people who are maintaining and developing with Dask, they work at our organization, other organizations, there's people all over the place working on Dask. And so it's a very vibrant community. There are 2 key things to keep in mind when you're thinking about what parallelization in Python really means. So when we talk about distributed data objects, that's one way that you can implement parallelization. You can take your data, you can break it apart, and we'll talk about this more in a moment. And then you have multiple data objects that can be stored, say, on different machines, thus not requiring you to have the single amount of storage for your entire data set in one place. I've been working on a forecasting project for a retail sales application, and I have 12 million rows of retail sales data that doesn't fit on my laptop. It doesn't fit on the single machine that I have available, but that doesn't matter because I'm using a distributed data source. So I just divide it up across all of my workers and carry on just as though it was smaller. Distributed computation is the other angle on this, and that is implementing the concept of delayed tasks. So you take a function, and instead of running it eagerly, so running it so that the return is immediate, you run it delayed so that it's sort of frozen in amber until you indicate the computation should happen later. And so then you can run those tasks in parallel at a later time rather than running them all at once the moment you have indicated. So let's talk about this distributed data concept first. I've explained a little bit about it, but this may still be a little confusing. Conceptualize it as you have pandas data frames that can be aggregated together into a Dask data frame. A single Dask data frame is literally this is not a metaphor, this is not figurative, this is literally a compilation of pandas data frames. So if you're using a Dask data frame and you have partitioned it across, say, 5 workers in a cluster, you have 5 pandas data frames, 1 on each worker. And that's really what you're dealing with. And so if you were to use what we call the compute method on your Dask data frame, it will take all those pandas data frames, smoosh them together into one pandas data frame and return it to you. But they're not just emulating the pandas API, which is definitely a part of Dask's broader ethos, is that they want easy access, not having to relearn, rebuild the wheel. Pandas API is common and widely used. And so they try really hard, the developers of Dask, to stick as close as they can to the APIs we're already familiar with as Python developers and Python data scientists. So this is the way that I sort of mentally think about how distributed data objects work in Dask. There's not just data frames. Keep in mind, there are distributed arrays and things like that that you can do. There's what's called a Dask bag, which is sort of similar to lists. It's a little bit different because of the fact that it has to sort of deal with the nature of distributed data. But you can use NumPy objects that you would normally think of as unitary, so to speak. They can be distributed with Dask and that kind of thing as well. So the other side, distributed computation. When we're talking about this, I'm showing an example here of a task graph. If any of you have any familiarity with Airflow or Prefect or other pieces of software that are designed to implement task management or job management, this is the same kind of concept to think about. Dask will allow you to take a function that you've defined and then wrap it up in delay so that you can run it, but not run it, not actually evaluate it until you want to later. So you can create these graphs of, I would like to run, the loading function 25 times at the same time. You want to run the loading function parallel so that all the workers are all loading data at the same time, for example. Or you want to do, a grouping and aggregation step. You want to do that in parallel. You can do that as well. This enables you to sort of let Dask like it can explore the task graph that you've designed, the things that you've assigned to run, and it can figure out what should run parallel to in spatially, temporally, run parallel temporally to be the most efficient. So it will actually organize things and figure out what should run when and which workers, and do all of that distribution for you. So you're not doing the orchestration manually, which can be a real pain if you're dealing with other infrastructure types where you do have to do that manually. So those are the two ways that Dask can enable you to accelerate work. You either can work with more data at the same time without any loss of speed or any waiting around or that kind of thing. That means either a better model because you're not downsampling, or much faster development of a model because you're not, churning through multiple batches of data, one after the other ad nauseum. And then you've got this distributed computation task where if you have a really complex model, a lot of repetitive tasks that need to be done, say, ensembling, or if you're doing a hyperparameter tuning of a very, very large parameter grid, something like that, this is perfect for that, because then it can just run them all at once rather than, well, let's try, the learning rate of 0.01. Let's try 0.015. You can do all of those serially and it will get done and you will get to the same result, but it will take a tremendously longer amount of time. It also enables you to keep adding resources as needed. If you only can do one task at a time, really, there's no point in adding another machine to help you work on that task, because there's one task, one core, going to do it one at a time. Dask enables you to start dividing work among additional machines. And of course, with the availability of EC2 instances or Azure or other kinds of places where you can rent compute power by the minute, then that really enables you to scale it up to, the sky's the limit. And so what I'm going to show you in the demo later on is going to be a demo using a 6-worker GPU cluster. So that's 6 different GPUs all working together in this cluster to do this training task in parallel. But I'll get to that in a little bit. So to talk about a cluster, I think is also important, just so that we kind of understand what we're dealing with in the context. If you've done any sort of distributed data storage, or distributed computing, this won't be that complicated for you. But if you haven't, then this might be helpful to sort of think about in terms of the I like a visual. I'm a visual learner, and I find that this sort of thing helps me to just sort of frame it in my mind. So the client is what you would think about as either your terminal command line or maybe your Jupyter instance. I do a lot of work using Jupyter instances because that tends to just make the iterative process a little faster. but it's the location that you are interacting with as the end user. So envision a human person on the very far side of the screen here, next to the pink trapezoid. So then the client is actually communicating to the cluster through the scheduler. And the scheduler is a small machine usually that's been spun up along with everybody else. Every single one of these boxes is a separate machine. And so the scheduler might be, a medium large. It's not going to have a GPU on it because there's no need for it. It's not going to be doing anything except hearing instructions and passing them around. And then you'll have workers to the, n number of workers to your preference. These could be worker instances that are GPU enabled or not. You may not need GPUs for your workers. They're all going to be the same type of worker, but it doesn't really matter what kind of machine you use. I'm going to show you a little bit about this in a moment, but just to give you an example, this is the website that shows you EC2 instance types available from Amazon. And so as you can see, there's zillions of types. The compute optimized ones are in the C range. Accelerated computing are the P ones, and these are the ones I'm going to be using. One of these later. I'm going to be using a P, I think. There's also these G4s, and actually I might choose that. And we have access to all of these. So this is the kind of thing that when you're using a service like Saturn Cloud or others that give you a chance to rent the compute directly, choosing the worker size that's right for you is very simple. You don't need to understand a whole lot about the inner workings of AWS, which can be gnarly. In this case, you just choose, I would like this many GPUs and this much memory and this many CPU cores, and you carry on, or that kind of thing. So deep learning, how does this really relate to deep learning in particular? Because this kind of stuff that I've been talking about, say, hyperparameter tuning, it's deep learning related, but it's not, that's something that any data scientist, any machine learning engineer is going to be working with. I think that deep learning has particular advantages in using distributed compute and distributed data storage, because some of the data sizes in deep learning can be much larger than other things. The example that I'm going to show today and that I run into a lot is image classification, image recognition. I've worked on training an image generating GAN with deep learning and distributed clusters, and the speed gains that you can see are just mind-boggling, because the thing that you can lazily load the images, and we'll do that in this, so that you're not waiting for images to load so that your model can go ahead and do the classification task or that kind of thing. And then the complexity of models. The more layers you're starting to add, the more complexity inside those layers. You can start to get really complicated and just compute heavy training tasks, and the ability to distribute that across a cluster rather than having to just try and find the biggest single GPU machine possible is a really, it frees you up. It frees you of your possibilities, your opportunities to try and do training in different ways. So those are just a few of the areas where I think that deep learning in particular is really a great spot to try and apply Dask with the GPU resources, because you're already probably using GPUs for a lot of the training that you're doing, but there's nowhere, you don't want to go, where do you go from there? Do you go to TPUs and do you spend that kind of money? But why not try multiple GPUs first? And I think Dask is a great way to get there. So now I want to talk about distributed training, because that's the demo that I'm going to show today. And I want to give you insights to how it works under the hood before I start going into code and getting into all of that. This is the sort of thing that as not specifically a deep learning scholar was the most challenging for me to learn about this. And once I got it, it was just exciting, because it's really cool how it does work. So when we're doing distributed training, and this is all going to be a PyTorch example. So if you're more familiar with TensorFlow, sorry, this is going to be all PyTorch code, but I think that the underlying concepts should be applicable for different frameworks as well. You're taking a single model training, but you're using multiple machines to train the same training task simultaneously on different training samples. And that's really the underlying task. The issue is, okay, if they're all training and say different groups of images, so they've got, this one's got images 1 through 100, and that's got 101 through 200 and so on. How do we then smoosh it back together into a single train model at the end? How do we actually aggregate those? And that's the task that we have developed, that you use what's called PyTorch distributed data parallel for. DDP is what it's known as. And so I'm going to show you the workflow within the cluster. So remember the gray box with the yellow. This is another sort of design of the same concept. I'm going to walk you through how this all goes, and then we'll talk about that. So we've got the client back at home, which is you're working on the client, right? You're sending this data task to the scheduler, and the scheduler will distribute the task in question to all the workers. That's the hyperparameters you've chosen. That's what kind of, model architecture have you picked. I'm going to be using ResNet 50 architecture for the demo that I'm doing later. But it's, what are your evaluation metrics, all of that kind of stuff. That's the task that's being handed out to all the workers, and they're all being told the same thing. Hey, you're going to train this model, you're going to figure out how to identify images better, and we're going to give you a set of images to work with. So then one of those workers, as part of this whole task, is being assigned the main worker sort of mantle. And it is going to be the worker that is keeping track of the model state of all the workers. So as each worker begins, it loads its own data directly. So the worker loads the data directly, in our case from S3, but from wherever you're keeping the data that you're going to be training on. So each of these workers is loading a different sample from the S3 bucket that's been told to by the task that's been assigned. They'll run their training task as normal. And then at the end of each iteration, that worker will sort of collect up all of what it's learned from this batch and send it back to worker 0, the main worker. And then the main worker will average the gradients that everybody learned. And this is an example with 4 workers. You could have 400. You can have as many workers as you want. They can all keep working on this. It just depends how much training data you've got to work with. So when worker 0 averages that gradient values for the whole net, then it will distribute that back out to all of the workers, and that's broadcasting the model state. And then I'll start a new iteration from that point. So they're all adding, they're all contributing some slightly different learned patterns to the overall. And then they're all sort of getting the boost that they're learning from each other via worker 0, in essence. So with that, I'm gonna pause and mentally look at some of our chat questions, and then we'll go on to showing the demo, which is going to be an example of using the ResNet 50 model. I'm not going to use the pre-trained version in this case, but I do have the ImageNet pre-trained version that obviously does quite a bit faster, because I'm using the Stanford Dogs data set, which falls under the ImageNet label set. But so let's take a look here. Okay, chat questions. Can I comment or compare Dask to Ray? I don't have a lot of experience using Ray. What I've heard is very nice, and that they've done some really cool work with it as an element for doing parallelization as well. But I honestly don't have a lot of personal experience that I could speak to as far as how it's distinct. So I don't know that I have a lot that I can help you with on that, but I do have some colleagues who have more experience specifically with Ray, and so I can put you in touch with them if you like. Yanni, if you want to send me an email or just put your email in chat, I can get you in touch with somebody who can give you a little bit more information about the differences. Is this analogous to federated learning, except you're doing this in order to parallelize? Yeah, I suppose. The gist of this is that it's really keeping the training task very centralized, so that each worker's divergence is getting sort of aggregated back into the whole at the end of every iteration. Okay. Sorry, I'm just getting distracted by the next question. I apologize. So what you're getting the ability to train on multiple workers at the same time, but they're not getting very far apart, is I think a key thing to keep in mind, that they're really getting brought back to the ranch at every iteration, and so you're not going to have to worry too much about the aggregation later. So. How are Dask bag partition counts optimized? Well, I'm not using a Dask bag in this situation because I'm using the Dask data frame, of course, a different kind of Dask data object, right? I think that it depends. In general, the partitioning of Dask objects depends a lot on what kind of workers you have, what kind of tasks you might need to run on them. Having the most partitions possible is not necessarily going to be a good idea, because at the point where you're running a task across all of the workers, if you need to, if your data needs to understand each other, so for example, if you're doing a group by or an aggregation on your data, that's easy to do with Dask. There's no problem with doing that. If you're doing joins or things like that, Dask can handle it all. But the more distributed partitions of the data that you have, the more cross-worker communication needs to happen, and that is the time when things can get a little bit slow. So I would say that you want to, it's a bit of an art to figure out exactly how many partitions you want for a particular data object, because going to too many partitions can start to slow you down because you're initializing more communication across the workers than you would otherwise have to. Okay. I think that's the questions for the moment. So I will go ahead and move us along to the demo itself. So this is going to be showing you actually code in the Jupyter notebooks, and I'm running this locally. So this is Jupyter notebook just running on my local machine. I am going to be accessing a cluster that is remote. So I'll show you how this all works as we go. And this sort of technical aspect, if there's questions, please feel free to pipe up, because I do this all day, every day. So for me, there may be things that I say or forget to mention that are unclear. So call me out. So I'm using Saturn Cloud to access the GPU cluster, and I'll explain later on how that all works. But I have a Saturn Cloud account that is separate, and I'm logged into that account. And then I'm also going to be using the tool Weights and Biases for model performance monitoring. Saturn Cloud doesn't do all of that, but Weights and Biases is a very cool tool, and it's free, and they let you have tons and tons of models to, and they're not throttling your usage or anything like that. So that's the first thing to keep in mind, that these two free tools are being used, and so that's one thing to keep to pay attention to. Then I'm loading a few specific libraries that are these are the libraries that I suspect you might not use in a normal serial training process, a single node training process. So multiprocessing, which is going to be used for allowing us to parallelize the data loading step, the lazy data loading step, which I'll explain in a bit. There's a thread pool executor, which is related to making sure that all of the workers are able to keep track of what's theirs and what's not. So then the DDP pack module from PyTorch is the wrapper that we'll use to indicate that our model is going to have this parallel training and is going to be part of that architecture that I described previously. The single worker is the main worker, and then everybody else is communicating back and forth and the training and communicating the gradients. Dask PyTorch DDP is a library that our organization actually developed, an open source library that handles the process management under the hood without having to surface that to the user. So you can just distribute your tasks to the cluster without having to identify exactly which worker gets which task and things like that. We just can manage that under the hood, but it's open source and the code is available if you're interested. And so then just a few things, the Dask distributed library, there's a few pieces for that as well. I am using a separate file to import a few helper functions and some additional libraries. These are in the GitHub repo, so please feel free to check them out. You'll find it under functions.py. Just a few functions here. There are a few different things that I'm doing in there. I'm label formatting. The labels that I have on this particular version of the Stanford Dogs dataset are a little wonky, so they need a little bit of fixing. Some data pre-processing, which I would normally talk about, but I really want to make sure that I give to the actual discussion of the training flow for you guys. So I'm going to skip a little bit of the pre-processing element in order to make sure that we have time to look at all of the model training steps. But one of the things that this includes is implementing a lazy data loader, which I've shown a little bit of the code for here, using the multiprocessing context of fork, which is different from the normal multiprocessing context that you might use for PyTorch, but for Dask, to ensure that you can load all of the data to the different workers lazily but as fast as possible, we recommend using the fork context. If you don't, there's some little errors that may show up. But otherwise, this sort of thing is a data loader object like a PyTorch user would be familiar with. We're using the data object, the image file object. I can actually show you. That's called S3 image folder, pardon me. That's loading directly from our S3 bucket. We wrote this image folder data class because it wasn't available. There wasn't a native S3 data object that we wanted to have one. So it's available in the Dask PyTorch TDP library if you're interested. And then there's a few functions that I have in the end of the functions script, pardon me, for plotting results and for producing a sort of sample of the images and the labels that they've been assigned so that we can see that in the model performance management tool. So I'm going to go ahead and run these. I think they're all already run, but I'll just make sure. So then we're really getting very close to just going ahead and running the tool. So I'm doing the image pre-processing, making sure that my tensors are all the right shape, making sure my labels are all right, doing all that stuff. I'm doing that behind the curtain. So assume that that stuff has already been managed. I'm loading raw image files from S3, doing the transforms that I want, cropping, making sure the normalization is done and all of that. One of the things that I need to do before I start looping through my training function, which is going to include everything from load the image, transform the image, do the training, evaluation, split, and then train, is I need to make sure that device is identified as CUDA so that I can be sure that I'm using GPU resources wherever possible. If you already are doing your PyTorch training on GPUs, then this is old hat, and you don't need me to tell you about that. But just for your reference, I still need to make sure that everyone who's in my cluster knows that it should be using its GPU resources, because they all, of course, have CPU resources as well. In this section, I'm really just setting my model hyperparameters. There's nothing super fancy about this, other than I have set up a few things in my pre-processing steps to allow me to subset the data. So I'm breaking up my data into number of chunks that I have of workers. In this case, there's going to be 6 workers in my cluster. So that means that my 20,580 images, 580 images are being broken into 6 chunks, and those will be assigned to separate workers. And that's the way that I'm ensuring that my data is being, cast out and scattered to the correct workers, and not, everyone's not doing all of the images themselves. You can train that way. You can say every worker I'm adding to the cluster is going to run through all 20,000 images. And you can, there are things you can do to increase the learning rate to sort of make that still add efficiency to your overall process. It's not useless to do that. It's less common than the way that I'm going to show you here, which is breaking up your training data in order to distribute it to the workers. And then there's the usual things. I could downsample, I could change my train test, the evaluation split, and that kind of thing. And then I'm using this public repo to GitHub public S3 bucket to get the data. So this project ID is one thing that I should mention. This is an ID from Saturn Cloud. And so I'm going to show you now what the project is. I have this project called CDL demo. And this is the Saturn Cloud sort of environment. This is what you would find if you log into Saturn Cloud and go to a project you've created. If you're interested in more information about this, our website has tons of valuable information. We have documentation about all of the startup, all of getting your feet under you and figuring out how to use it. So please don't feel like this is intimidating or difficult to get used to. I'm not even actually going to touch anything in the UI, however. I just want to show you where it is and show you that it exists. But this Dask cluster that's running, I have started it up from my Jupyter notebook on my local machine, and I can shut it down from my local machine, and I don't actually have to touch anything in here at all. And that's one of the things that I think is just really cool about the product, is that you can use the UI if you care to, but if you don't, you can stay away. But this is the project ID that represents this project. You can see this URL, the number is the same. And it's just so that I can tell my notebook, and notebook can tell Saturn Cloud which project I'm trying to get in touch with. So now we're into the deep weeds. This training function is going to be a lot of sort of stuff that should be pretty familiar to anyone who's working in PyTorch normally. But I want to show you what I'm working with and how it all looks so that you can sort of see the differences and see what's distinct about this versus a single node training task. One thing that I'm immediately going to do is I'm going to get the rank of the worker, because remember, I've shown you the main worker has slightly different responsibilities than everyone else. And we need to keep track whose gradients are we dealing with at any given time. So if worker number 1 sends the information back to worker 0, it needs to know that it's still waiting for, say, workers 2 and 3. If it doesn't know that, then the process management can get very confused. Worker 0 and then everybody else, they all need to sort of have an identity that they can keep track of. So then I'm, catching up with my device, and then I'm loading from the Torch Vision library, the ResNet 50 model. In this case, I'm saying not pre-trained, but it can just as easily start with the pre-trained version, and it'll train much faster if I use pre-trained. I want to give you a chance to see more of the sort of longer steps. So then I'm passing my model to the CUDA resources, so making sure that it's going to train on the GPU resources, and that's important. And then I'm using this DDP wrapper, which I mentioned up above. As you'll remember, I loaded this from the PyTorch parallel module. And so now I'm just identifying my model as being trained in distributed data parallel so that all of the other stuff can run. From there, I've got a few steps that are about my model management tool, the weights and biases thing. You don't need to worry about any of that unless you're very interested in that. I'm setting my criteria, setting my optimizer, doing the normal things that you would do. I've got the preprocessing function that, remember, I have over in the functions module. All of this stuff is being defined, but it's not running until I get it out to the workers. So I want to make that clear too. So I've got the S3 stuff that is going to go there. I'm doing a train test split with the hyperparameters and the sort of criteria that I set earlier in the beginning before we started any of this. And then we'll just iterate. We're sending our model, are sending the batches of training data through the model and doing this the tasks, reporting back the loss correct, and so on at the end of each one. And now I've got an evaluation set that's just the same. And this is all identical to the way that the training set is running, with the exception of the model mode. So this is it. The really major things to keep in mind are just, we identify which worker we're on, and we add the DDP wrapper. Beyond that, it's not all that complicated. The training and test split, the pre-processing step is going to make sure that we get our downsample or subsample to the right number. So we're getting 1/6 of the data, not all of the data. There can be overlap. It's not necessarily a wholly unique subsample for each worker, but that's really okay in the way that we're training a model for this image classification task. Some of them having overlap and some not is as algorithmically not a problem. You can, however, try to designate that each worker gets a wholly unique data sample too. If you're interested, you can do that. But then the last real, let me run these things so I talk about them and I forget to run them. Okay. So then I've already logged into the model monitoring tool, which we'll see over here in a moment. And so I'm setting up my external connection to Saturn because I've got the project ID, but I haven't actually told anybody that I want to do any work here. So I'm setting my project ID, and then I have a user token, which is a private token that identifies your login. And so this is one of those secrets that you definitely don't want to store in GitHub or in plain text, so that you can make sure that it's kept secure. But now I have an external connection from here as my authenticated user to the project that we looked at momentarily. And now I'm setting up a cluster. So this cluster is already running, as you saw, but I could start a brand new one from here. I just need to identify the connection. Which project am I using? Workers, worker size. Remember, you can choose your worker size from this kind of library over here. And then the scheduler size, smaller, and then the threads. So once I run this again, it should still be running. So there shouldn't be anything particular. It's going to kill me the IP addresses for all of them if I want to. And then I have a Dask dashboard, which I can use to monitor the performance of the Dask cluster as it runs. Now, I'm not actually going to bother with that because we don't have a lot of time. But so now I'm using the dispatch.run function, which comes from the Dask DDP, Dask PyTorch DDP library, passing it the client, which I just created up here, which identifies which cluster I'm using, passing it the function that I defined here, this function, cluster transfer learning. And then I'm adding the model parameters, which I defined up above as well. And that's all I need to pass to it. So it's going to create one future or one running task for every worker that I have. So as you can see, there's 6. And now if I was to run, then I would get the identify that this has been given a task that it knows, like has an identification, and it's running right now. So now we can go over to the demo side and look. I have a few runs already pre-finished that you can see, but the one that we have just started is this one. And apparently it's been named Crimson Monkey. And you can't see a whole lot running right now because it's just getting started, but you can already see system utilization metrics. And this will start to fill in faster than the actual model performance metrics. I don't know how fast it's going to run today, but usually it takes a couple of minutes for it to get moving, and then you'll start to see model performance metrics coming in. While we wait for that, and then I'll try, before we close out at the very end, after all the questions, I'll take a chance to look at it and see where we've gotten to. But what we can see here, for example, is the previous run. This was a run that was using pre-trained. So this was one that already started at pretty decent performance. And so we can see the metrics. It did 6 epochs with this. These are the validation metrics at the top and the training metrics at the bottom. And these spaces in between are when it switches over to a validation set. And then when I switch back to training sets. So you can see that kind of, if you look at the numbers, they're actually alternating back and forth between validation and training. You can also see the images themselves. This is always fun. Everybody likes to look at dogs. So you can see how the model is performing on these. If we look back much further in the media, oh no, I did the wrong thing. If we look back much further in the media, we'll be able to see where it was doing poorly before. I'm not sure if where I can go to see all of the old ones, because it doesn't want to show you the old ones necessarily. Let's see what we got here. Come on, let's find one that it got wrong. Because at the end, towards the end, it always gets them all right. Here we go. So here's one that it was incorrect about the prediction quality. So this little four slot of images and the predictions and the color coding is one of the things that's in my little extra functions folder. So if you want to try and run something like that yourself, please feel free to borrow it. And we can look at system performance. So what we want to see is high GPU utilization while it's running. This is pretty good. We would like to see that GPU utilization as high as possible, because when your GPU is running, and it wasn't running at these later stages, it was just waiting for more input. When your GPU is running, you want it to be as highly utilized as possible, because that's expensive and you don't want it to run any longer than it has to. Let's see if the one that I just kicked off has anything new to report. Here we go. So you can see it's already running, and this is, it's starting not trained, so it's starting from, kind of a sad state, but we can watch the correct values increase and the loss decrease as you go, and you can just sit here and watch it, and hopefully it'll eventually start to get pictures correct. So that is pretty much the conclusion of the demo. I know that we are right at time, so I want to give you guys plenty of time to ask questions. One of the things that I just wanted to I want to go over a few quick notes at the end here. You can really implement this kind of cluster distributed training, or just implement Dask in deep learning really much more easily than you think. It's much more affordable than you think if you're renting by the minute. And I think that you can really see tremendous benefits from distributing, say, your hyperparameter tuning, distributing your pre-processing steps. I do a lot of that, even if I'm not training my model on Dask or using a cluster to train the model. Getting all of the data pre-processed can be a huge pain, and being able to parallelize that is a great advantage. Data loading speed can end up being the slowest part then. Data loading speed can be the part that needs optimization when your model trains so fast, because you have implemented a parallel system like this. And then make sure that you're employing those GPUs to the full potential, so that you're not, loading up a GPU that you don't actually need or don't have use for. Beyond that, thank you so much for joining me today. I hope this has been useful. I hope it's been inspiring for you to take back and use in your own training work. And if you have other questions, please feel free to pipe up and let me know, or get in contact with me after today. But with that, I will stop sharing my screen and we can just have a chat.
Thank you very much, Stephanie. So audience, please feel free to ask questions either by voice or put them in chat. Any questions?
I don't see any in the chat.
Yeah, I don't see them either. So I actually do have two questions. So at the beginning, you mentioned some SQL code on top of Dask. So does Dask come up with its own SQL engine, or how does that work?
So no, it doesn't by default have its own SQL engine. However, there is a companion open source project that is trying to implement Dask with SQL, or SQL into Dask. We have found in our own work that a lot of our customers or people that are using Saturn Cloud like to do to incorporate a Snowflake with Dask, and those are really well coordinated. And so you can use Snowflake integrations and do sort of the SQL level aggregations that you might want to do and that sort of thing on that side. It's an interesting question. It's something that we have definitely talked about, but there's not a native built-in SQL engine in Dask at the moment, no.
Okay, so staying on the same topic, are you aware of any benchmarks when it comes to performance of Dask with one of the SQL project that you just mentioned versus, for example, Spark?
Off the top of my head, I'm not sure. I can take a look and see if there's anything that I overlooked. But because I feel like one of my colleagues did write something about this, but I'm just trying to recall if I have a link to it.
If you're not aware, so I
can track something down and send it to you to distribute to the group afterwards. So let me make a note.
Yeah, and so my next question is also related to Spark. And that is, so Spark has Spark streaming. Is there something analogous in
Dask? I'm not quite sure in what functionality are you looking for, I guess.
Well, okay. So let's just say, so in Spark, streaming now in the last versions of Spark, streaming is essentially an infinite data frame.
Sure.
Right. So infinite in a sense, kind of FIFO type, let's say, infinite data frame.
Yeah.
So can Dask accommodate this kind of a setting, so an infinite data frame, or something like similar concept?
Yeah. So if I am understanding it right, so the idea behind this streaming is you can load it on an infinite basis, but the manipulation and like aggregation and things like that can be a little weird to do on a streaming data object by its nature. And so our experience at this point is that fully like absolute streaming data is not honestly, not a lot of people actually need it for the things that they're trying to do with Dask. It's not that it's straight. Well, I can say straight out, streaming is not a feature of Dask at this time. It is, however, a different kind of concept for thinking about how you store and manage your data. Because when you're talking about distributing data across workers, the number of workers you can have to distribute your data across, that can be infinite. There is no necessary limit to the number of workers you can acquire and rent out to distribute your data across. So there's not like a size limit inherent to Dask. I think that the framework of conceptualizing your data as distributed and then using the sort of architecture of Dask, I think it makes more sense to me mentally when I'm trying to think about how to work with my data. But I think being able to do large scale data processing I think it's easier with Dask because you're adding those resources to scale and scale up the data processes you can do, as well as just having more data there, because having it is one thing, but being able to actually use it and actually manipulate it to the way that you need it is sometimes another.
So thank you. So okay, so my very last question, and you kind of touched upon this at the beginning. Can you name, say, a perfect or a few perfect use cases for Dask?
Oh gosh, there's a lot. There's a lot of use cases that we found. I think that for this sort of image classification work, that it's incredibly useful. I can't imagine trying to do this one image at a time, or even loading them all at the same time. We have found some really great applications for just data pre-processing. As I mentioned, I'm doing a project with retail data where there's just no way I could pre-process the volume of data down to train the model that I want without being able to do distributed. There are libraries that are that enable any kind of basically any machine learning you do with scikit-learn has been ported to Dask. So there's an assortment of Dask libraries that are specifically designed to emulate the scikit-learn experience, but actually distribute it and also make it GPU accessible, which is a really exciting opportunity. So you can have distributed data, distributed compute, and on GPUs, all with the same sort of API that you're familiar with from scikit-learn. Let's see. It's mainly, there's a lot of use cases that we have found. There are a lot of cases that our customers have found. Super high grain data, very small data grain tends to be a big problem when you're trying to do, say, large scale modeling, because you can't load enough of it in memory at one time to build the model that's going to be successful on the next chunk. So being able to have a larger data set without needing to find the biggest supercomputer around means that you can train a better model without having to sacrifice from some other area, whether it's the budget or the data quality. Yeah, I think we find that a lot of people like it for deep learning. A lot of people like it for the pre-processing steps and just plain old data cleaning and the stuff that's not very glamorous, but is really absolutely necessary in order for the model step, and the fancy stuff later to be successful. And I think that that those are some examples. We have some blog posts and things on the Saturn Cloud website to talk about specific use cases. We've gone through examples and built them out ourselves to make sure that customers have, information about what they might try to do.
Okay, thank you. So audience, any other participants, any other questions for Stephanie?
One person asked for the URL and I accidentally sent it to another person. And so Holly, thank you for sending that to the rest of the group. I appreciate that. Yeah, if anyone has questions later on, let me know. Feel free to get in touch.
Is there, okay, so my very last question. Mm-hmm. Is there a company behind Dask? I don't know, Confluent behind?
There are several companies that do Dask related services and provide Dask tools. We're one, and there's an assortment of others, but Saturn Cloud just happens to be one of the companies that is trying to bring Dask out to, and sort of bridge the gap between the development and the sort of Dask developer open source community and sort of enterprise customers. But Dask itself is a fully open source community developed project. And so there is no single business managing or keeping Dask.
Okay, thank you very much. So participants sort of vote in chat whether Stephanie should get a big mug from Northwestern, or if you have more innovative ideas for what kind of a gift to give her, post on chat. So I learned that she loves her current mug, so maybe it's time to replace the mug. All right, so Stephanie, thank you very much. So I'm positive that the audience found the talk very informative, or not informative, but also that they gained a lot of knowledge. So I definitely did. Yeah, so we all, on behalf of the entire center, we thank you very much, and we appreciate your taking the time. And I hope to meet you in person I'm not going to say one of these days, but let's say in a few months or so.
Yeah, I can hope so.
Yeah.
All right.
All right, well,
Yeah. So thank you very
all.
much. Yeah. Thank you. We really appreciate it.
All right.